Good morning, fluid mechanics students. Sorry, I'm so late doing this lecture, but this term, that's the way it's been, I know. So probably going to produce this one and another one and talk about open channel flow. That's one area we need to get through, at least at the basic understanding. And then sheet flow, regular stormwater runoff. So open channel flow is later in the book. I'm going to flip you around. So it starts in chapter 6. And we're just going to do a portion of this. But you can see that it talks about computing the slope of a channel. That's pretty straightforward. Compute the cross-sectional area, the wetted perimeter, that's the part that's wet of the perimeter, and the hydraulic radius. So that's all very straightforward. Normal depth and critical depth is a little more problematic. So let's do it. They call them weirs. You can call them channels, troughs, whatever you want. But it is a method of transporting water, right? It can be transporting water along the side of a road, like a ditch, or it can be transporting water for irrigation purposes. We transport water very long distances this way. So obviously it's a calculation that involves slope and also area and depth. So if you know those things, then if you have a velocity, you can come up with a volume flow rate fairly easy. So most of these types of system are turbulent, believe it or not. Really, the only time we get in laminar flow is in sheet flow. So that's like rainwater runoff in a parking lot. That's a sheet of water. That's pretty laminar flow. But the flow in a weir often looks like this, where we might get 2.5 feet per second in the middle, but on the edges, we have almost zero velocity. So then there's a gradient from kind of the geometric center towards the critical depth height is the maximum velocity up in this region, right? And then as you move away and get next to the concrete, a lot of these are concrete, some are metal, some are dirt. Then those are very rough surfaces and the velocity goes to zero. So, like I said, slope is important. So the first thing they have you calculate is the slope. And the easiest way to get slope is if you know a length of your weir or trough, then you also need to know the elevation change in that length, and then you can calculate the slope. It's a pretty straightforward equation. So they show you that equation here, drop over length, right? That gives you slope. So notice it's unitless, S sub O, because it's usually feet divided by feet or meters divided by meters. So the other thing that we need often is the area. So cross-sectional area, you can look up these cross-sections. This is a cross-sectional area for a trapezoid. Trapezoid is a very common weir. That's this thing. But a pipe, the area of a pipe. A natural stream or a natural ditch is much more difficult to find the area and the wetted perimeter because it's just not defined. So most of the time, we draw those cross sections best we can, maybe in a software, and get an area, based on that. All right. So the hydraulic radius, R, is the area over the wetted perimeter. So this is called hydraulic radius, and it just gives you a sense of kind of the efficiency of the hydraulic channel. Okay. So it's cross-sectional area A divided by the wetted perimeter. And again, the wetted perimeter is the perimeter that's wet, right? So just the portions that's wet, not the portion that is out of the water. All right. So pretty straightforward, given the information, you can get the wetted perimeter and the hydraulic radius. So as we move forward, the next thing we really need to know is this normal depth and critical depth. So you can read through this to talk about that talks about the normal depth, but the calculation we're going to run typically is the critical depth. So this has to do with energy within the stream. So the specific energy diagram is down here, and this is a critical depth versus minimum energy. So that's the flow you want. You want the minimum energy within a water transportation system of this kind. If you're expending a lot of energy, then you're going to lose your velocity much faster, and your flow is not going to be anywhere near the flow that you want. So the purpose of these systems is to transport water, and we want to transport that water as easily as we can, okay? So this is the energy grade line. So depth equals energy straight line. And this curve, you know, starts to join that. But where it comes around and curls at this minimum energy efficiency, that's where we want to get the critical depth. That is kind of the definition of the critical depth. Okay. So if your weir is too steep, you have too much velocity, you're not going to transport water very far that way. If it's too flat, you don't have enough velocity. You're also not going to transport water well that way. So we want to know this happy location, right? So you might read about this because they do talk about different flows, subcritical flow and supercritical flow. Not as important with us, but critical velocity is important, right? So the critical depth is called, the velocity at the critical depth is called the critical velocity. When a channel has a slope that causes normal depth to coincide with critical depth, the slope is called a critical slope. And that critical depth is computed by the following relationship. This relationship has to do with area, flow rate, gravity, and T, the top width of the channel. So that's very interesting. So these are things that could be measured, right? So in the problems, they're going to give you things like the top width of the channel, and they might have you find the critical depth. So the DC critical depth equation is here, right? Notice that it's the cubed root, and this is for rectangular channels. So it's different for different channels, all right? And the book does go on to talk about like non-rectangular channels, and it'll go through some examples. So you'll be able to see, I'm not going to do it because you'll be able to see kind of how to go through this. This is a find the critical depth problem, right? Find the critical depth in a trapezoidal channel where we know things. We know the bottom is 6 feet. We know the slope on both sides. We know it's lined with concrete. So that information is good information for us. Let's see here. Yeah. And then they just go into these example problems and then the homework. So I think you'll be able to work your way through this. There's also the Freud number. So this number is used to understand the difference between subcritical flow and supercritical flow. And again, it's for a rectangular channel. So many of these equations are for specific types of channels. So just zoom into that and just go for it. So it is a process of trial and error, believe it or not, when it comes to like a weir. So it's interesting because as they go through this, they're going to say, let DC equal 1 foot and then run the numbers, right? So the thing that they're trying to understand and compare is, you'll see it at the end, they're going to come up with these different 199, 2, and 571 numbers, and then they're going to try to interpolate between the two. So it's pretty complicated when it comes to a weir channel, right? So you're given a slope of 1%. The channel is lined with concrete, good condition. and it carries a flow of 880 CFS. So we know the flow rate, we know the wetted perimeter, we know gravity, right? We can calculate this 199 number for Q. Okay. So this side of the equation is the 199. So the Q squared over G, 199. So it says this value is meaningless. It's got units to the fifth. So then they go on and say we choose various depths, each value computed with this A3 divided by T. So this is all going back to this equation here and breaking down Q and breaking down A3 over T, right, which is Q over G. Anyway, so then they say, okay, trial one, we let the depth equal to 1 foot. All right. So then A is this, and A cubed is this. The geometry of the channel gives T to be 10. So a lot of variables, but T is the top width, right? So if we know that it's 1 foot deep, we can calculate this top width at 10 feet. All right, so then now that you have those numbers, you can run this A3 to T and get 51.2. So then it says this value is compared to the value of 199 already computed, blah, blah, blah. Since the value is less than 199, choose a higher value for this number. So then we say, okay, let DC equals 2. So then they go through the same calculation, and instead of for the A3 cubed over T, they get 571, which is larger than 199, obviously, greater than 199. The correct value of D lies between these two. Now, it's a big range, though. 571, right, to 51.2. It's big. So, since it became larger than the 199, we know that the 571, that the correct answer is between the 571 and the 199, right? So then they do the interpolation. So if you don't remember interpolation, this is the equation that does it for you. And then it comes up, you can interpolate between the two, and DC equals 1.28. Pretty inaccurate method, I think, but it does work. And that's how they go about it in this book. That's a non-calculus way of doing it. You're not going to do that, but I wanted to walk you through one of these. You're going to do just a regular rectangular problem. So I chose this one, which is a pretty simple one. So, all right, that's good. Good luck with it. Let me know how it goes, and then I'll do a little more on rainwater runoff in probably I'll try and do it early next week. I really will. So thanks for your patience.